All right, and so in this video, we're going to go over the projectile motion midterm review. So this is the second to last section on the review packet, right before forces. So the projectile motion is really just a continuation of the one-dimensional kinematics that we just talked about. For projectile motion, you're going to have quite a few conceptual questions on it, and we're going to try and go over some of those now. And there'll be 2 free response questions. So there'll be a horizontal launch and a ground-to-ground angled launch. We'll go over an example of both those in this review. All right, so let's look at some of these multiple choice questions. Kind of go through them one at a time here. So in general, for projectile motion with no air resistance, the vertical component of a projectile's velocity. And then they have, sorry, just trying to get it on here. Looks like I'm gonna zoom out a little bit more. Okay. So if we look at no air resistance, that's key here. No air resistance means that the horizontal component is not slowing down. We're looking just the vertical component. So this is the velocity as the projectile goes up and then comes back down. And so in this case, we're looking, at just how does it change as the projectile goes up, turns around, and then comes back down. So the key here is that at the very top, the velocity is 0 in the y direction, which means that the component of the velocity is changing. It's going from being positive upward to 0, then to negative coming down. And so it changes due to gravity. That's letter A. Number 2, in general, for projectile motion with no air resistance, the vertical component of the projectile's acceleration. So here we're looking for as opposed to velocity, number 1. Number 2, we're looking at the acceleration. And this acceleration is going to be a constant. It's going to remain a non-zero constant. So the acceleration stays as a negative 9.8 meters per second squared the whole time. The vertical acceleration. In general, projectile motion with no air resistance, the horizontal component of the projectile's velocity. So again, we're looking at the velocity, but this time, as opposed to the vertical, which we looked at in the last 2 examples, now we're looking at the horizontal. So the horizontal component of the projectile's velocity is going to be a constant all the time, because we have no air resistance. So this will remain a non-zero constant. It doesn't change. And because the acceleration is 0. So the acceleration in the horizontal direction is 0. So that's 2 of the main concepts in projectile motion. In the vertical direction, in the y direction, there's a constant acceleration due to gravity, which means the velocity is changing. It's decreasing on the way up to 0 and then increasing on the way back down as it gets faster and faster. For the horizontal component, it has no acceleration, which means the horizontal speed is consistent, it's constant, and it doesn't change at all. Okay. Question 5: what angle should a kicker try to kick a football to kick it as far as possible? So we talked about this in class. 45-degree angle gives you the most range. All right. A ball thrown horizontally from the edge of a rooftop at the same instant a second ball is dropped from the rooftop, which reaches the ground first. So we're looking really at kind of this scenario here where we have one thrown horizontally this way, and at the same instant, maybe one just dropped straight down. Sorry, I shouldn't draw that arrow. It's really just dropped with no velocity. So this one begins to increase in speed as it goes toward the ground. This one is going off to the right as it begins to increase in speed and go toward the ground. So they're going to hit the ground at the same time. So C. But when we look at the ball thrown horizontally from the edge of the rooftop and which one's traveling faster, because the thrown one had a larger initial velocity, it's going to have a larger final velocity. It's going to be traveling faster. So the thrown ball is going to be moving faster, but they are going to be reaching the ground at the same time. And to explain that difference is that the distance traveled for the thrown ball is going to be further, because not only did it go the same height difference here, but it also traveled a further delta x, whereas this one, if it's just dropped, will go straight down. All right. The next four problems all deal with a cannonball launched on a flat firing range with initial and horizontal velocities of 60 and 80 meters per second. If you hear the jingling in the background, that's my dog rolling around on the ground. Fun times. Okay, what is the overall initial velocity of the cannonball? So it tells us that Vix is 60. That's this component here. That's horizontal. And the VIY is 80. That's the upward component. And so my initial total velocity is the combination of these two, which is 60 squared plus 80 squared. Square root, just fine from adding those two vectors together. Or 100 meters per second. Don't add them together, just with simple addition, because they're not going in the same direction. All right. Part 9, what is the vertical velocity of the cannonball when at a maximum? When at the max height? So this is basically asking what's Vy when the cannonball is at a max height. And when we're looking at vertical velocity, remember, vertical velocity is what changes. So as it goes up, it reaches 0 at the top. So when you're at max height, the vertical velocity, that's Vy, is equal to 0. But the overall speed at the max height, so this 80 component went to 0. So this part here, that goes to 0. All that's left is the 60. And so that means that my overall speed when I reach the top is just the horizontal motion, the 60. And then the acceleration of the cannonball when at max height, the acceleration really anywhere along this is going to be negative 9.8 meters per second squared, always. Okay, so that's some of the basic concepts there. All right, now let's move into some of the problems. Again, the projectile motion is going to have a couple problems here in the exam. It's going to have a horizontally launched one like number 12, and it's going to have a vertically launched one like 13, or an angled launch one like 13. So we'll look at number 12 first. And it says a tennis ball is thrown horizontally from a 25-meter cliff with an initial velocity of 10 meters per second. Calculate the time it takes the tennis ball to reach the ground, how far away the tennis ball will land. So 2 things here. To start, draw the picture. So we got a 25-meter cliff. And the ball is being thrown from the top horizontally. So from this picture, I know that my height of the cliff is 25 meters, the velocity is 10, and I want to find the time it takes for the projectile to travel along this projectile path until it hits the bottom. Okay, and so I can think of it in terms of the y component and the x, the y and x horizontal and vertical motion of projectile motion. So looking at this, I know that delta y is negative 25 meters. I know that I'm starting from a max height and falling 25 meters, so I have a negative. And I also know that my velocity in the y direction as I start, because I'm at the top of my projectile and it's being thrown horizontally, is 0. Okay. And furthermore, hold on a second, I'm going to fix the setting here, give myself a little bit more room. Okay. Sorry about that. So where was I? VIY is 0 because my ball is moving horizontal initially. No vertical component of velocity. And so I'm looking for the time it takes, t, given these 2 things. And I'm also looking for how far the tennis ball will land, which is going to be delta x. So in the y direction, I have 2 things. And the other thing that I know, because it's in free fall, is that acceleration is negative 9.8 meters per second squared. So when you have those 3 things, you can look at your kinematic equations, figure out which one to use. The one you want to use is the one without v final, which is this one right here. Delta y equals VIYT plus 1/2 AT squared, negative 25 for delta y, 0 times time, plus, and then 4.9 t squared. Now the 0t cancels out. 0 times time. And so I'm just left with negative 25 equals negative 4.9 t squared. I can divide by negative 4.9 to both sides and then take the square root. And you get t equals 2.26 seconds. So that's the time it takes to reach the ground. Then to figure out delta x, it's quite simple. We just simply take the time that we had from the y component and we multiply by our horizontal speed of 10 meters per second. And so my again, going back to like speed equals distance times time, or velocity equals displacement divided by time, when you don't have an acceleration, so this is true for the x direction in projectile motion. When ax is 0, you have the speed of 10, delta x, what we're looking for, time of 2.26 seconds, which means that delta x is 22.26 meters. All right, moving on to, so this is the horizontal launch from the top of a building. Okay, so the other type of projectile motion problem that's going to be on the midterm is the angled launch. So here, this is example 13. The soccer ball is kicked along a flat field with an initial velocity of 15 meters per second at an angle of 30 degrees above the horizontal. So this is the type of problem where you have the flat field, it's launched at the angle, it's going to travel like this, come back down and hit the ground. Right? We want to know something about the max height that the soccer ball will achieve. Right? That's part B, and then how long it's in the air before landing and how far will it go. So we want to find the range, we want to know the time it takes, the height it reaches, all that. Okay, so to start out these, it asks, what's the initial horizontal and vertical components of velocity, VIX and VIY? This is your sine and cosine part. So this is where you take the angle and the velocity they give you in the problem, angle of 30 degrees, velocity of 15, and you plug it into your sine and cosine functions to break that vector down. Because really what you're doing is you're taking the 15 meters per second, which is at this angle, and you're breaking it into these two vectors, x and y. VIX is the cosine, so it's 15 cosine 30 degrees, and VIY is 15 sine of 30 degrees. All right. So for VIX, you get 12.99. And for VIY, you get 7.5. And we'll be using these numbers later. Again, this is our horizontal component and our vertical component. All right, and then in part B, it asks what will be the maximum height achieved by the soccer ball. So again, when we look at our picture, we're looking for delta y. This should be a positive number because we're starting from the ground here. We're just looking for how far up did it go. Positive change in delta y. The key here is, again, knowing that at this very top point, that Vy is 0. So we're going to make this be our initial and this be our final for part B, which means we can say V final y is 0. Okay. So we have the V final y is 0. We're looking for delta y. We know acceleration is negative 9.8. And we have VIY. VIY, which we found in part A, was 7.5 in the positive direction. All right, so I'm just going to take all that and I'm going to plug it in to one of our equations, the one that does not have time in it, which is the VFY squared equals VIY squared plus 2A delta y. And I'm solving for delta y. V final is 0. V initial is 7.5. acceleration is negative 9.8. And delta y is unknown. Square 7.5 and then add it to the opposite side. Divide by 2. And divide by negative 9.8 to solve for delta y. And you should get that it goes a height of 2.87 meters. All right, part C asks, how long is the soccer ball in the air before landing? So now we're looking for this time right here. So we know it's going to start here. Now let's make actually so let's make that our initial time. And now let's make this our final point when it hits the ground here. So here my delta y will be 0. And my v final isn't 0 this time. My delta y is going to be 0. All right, and so we can solve for how long it's in the air for. So we know delta y will be 0. We still have VIY as 7.5. And we still have acceleration as being negative 9.8. And so now I'm taking these three things, I'm solving for time. The equation that does that is the one without v final in it, which is the delta y equals VI y times time plus 1/2 AT squared. So VIY is 7.5, delta y is 0. So I get 0 equals 7.5 t plus 1/2 negative 9.8 t squared. Solve this equation, multiply through and subtract the 7.5 t over first. And multiply through, and you get negative 4.9 t squared on the right and negative 7.5 t on the left. You can divide by a single t. That gets rid of that with the square. So I'm just have a t on the left-hand side, and then I can divide by negative 4.9. So t will be 7.5 divided by 4.9, or 1.53 seconds. And then finally, how far away will the soccer ball land? So now we're finally looking for the delta x. And here we need to go back and, okay, we look at VIX. Remember that we found VIX in part A to be 12.99. That's important because that's how far it's moving. It's moving 12.99 meters every second. Now, if the time that it's moving is 1.53 seconds, as we found in part C, then the distance that it goes in the x direction is simply velocity times time, speed times time, or 12.99 meters per second each second for 1.53 seconds, or 19.87 meters. And that's how you do the angled launch problem. Okay, so make sure you study both of these problems here. Okay, make sure you know how to do the projectile motion one, angled launch, and make sure you know how to do the horizontal launch from a cliff.